Chapter 6, Lesson 1, problems we're going to do right now. This first one is going to be the more difficult one. It is going to be pretty much like 90% of the problems that you'd get from this section. And then the second one will just be a really easy one that's kind of like the other option that you could get. So our first problem has a tennis ball, and it's thrown towards a vertical wall with a speed of 21 meters per second and an angle of 40 degrees above the horizontal. So I'm going to try to sketch that. 21 meters per second, and then 40 degrees above horizontal. The horizontal distance between the wall, so I'll just draw kind of a line for my wall over here, and the point where the tennis ball is released is 23 meters. At what height above the point of release does the tennis ball hit the wall? One important thing they mention here is that get out. You guys want to meet my cat, who's currently knocking everything down. This is Stella. Stella, say hi. Okay. Sorry. Okay, so how high above point of release? The point of release is important because then we can ignore how tall the tennis player is, because otherwise it would hit at a higher point on the wall if we included the how tall the person is. Instead, we can just pretend the ball is released from 0. The second part asks, has the tennis ball already passed the highest point in its trajectory? You guys know that if we were to just throw a tennis ball, we'd get some kind of parabola. So it's basically asking, have we hit our apex yet? So the first thing we need to do is we need to split this 21 into our x and y components, and we'll use that using our ax is equal to a cosine theta, and our ay is equal to a sine theta. My a is the thing I want to break apart. In this case, that is 21, so 21 will be in each of these. Just like in class, we talked about how theta is measured from the positive x-axis. Here I have my positive x-axis, so I'm going to go cosine of 40 and sine of 40. Doing that, I found out that my a of x is 16 meters per second, and my a of y is 13.5 meters per second. So the first thing I need to figure out is my time, because in order for me to figure out how high the ball is, I need to figure out how long the ball is in the air. I can do that because I know what my change in x is going to be, and I know what my velocity in the x vector is going to be. So my distance of x is going to be equal to 23. My velocity in the x axis is going to be 16. And we all know that v is equal to d over t. So if I take my distance divided by my velocity, I get a time. And the time I get is 1.44 seconds. And we talked about today how time is going to be both the same for x and y, so I can bring that over when I'm solving for things in the y part. So at what height does the tennis ball hit the wall? So we know that the tennis ball is going to hit, and we'll call this problem 1. We know the tennis ball is going to hit the wall 1.44 seconds after it's released. We know this is going to have an initial y velocity of 13.5 meters per second. We know it has an acceleration of negative 9.8 meters per second squared. What else do we know? We know the initial position is going to be 0. We don't know the final position because that is what we want to know. So I'm going to kind of draw a line underneath him. My time initial could be 0. Time final is 1.44. We don't know velocity final. So that's pretty much all the information we're given. I don't really need to find velocity final at this point, but if you look at your equation sheet, you'll realize that we need to use our equation that goes xf is equal to xi plus vi tf plus 1/2 a tf squared. Our xf is what we're trying to find, so that's perfect. We're going to call him x. Xi is 0, so we can ignore that guy. He's 0. My velocity initial is 13.5, so I'm going to take 13.5 times my time of 1.44. 1/2 a means we're going to go negative 4.9 because negative 9.8 times 1/2 is negative 4.9. And we're going to multiply him by 1.44 squared because that's our time squared. When you plug all of that into your calculator, you find out that we hit the wall at a height of 9.3 meters from where we released it. So that's our answer for number 1. I'm going to erase a little bit of this over here so we have room to solve the second part. So the second part asks, has the tennis ball already hit its highest point when it hits the wall? And we have to justify that answer. So I'm going to rewrite all of the things I know and the things I don't know. We know the velocity initial in the y is going to be 13.5. I actually know my velocity final at this point is going to be 0. So I do know velocity final. I don't know what time, so the way I'm going to find it, and there's a couple ways we could find this. I'm going to ask myself, what time does it take to get there? Because any time after that time, the ball is going to be on its way down, and until that time, it's going to be on its way up. I do still know acceleration, that's negative 9.8. And with those variables, I can set up VF is equal to VI plus a change in t. VF is going to be 0 is equal to 13.5 minus 4.9 t. Sorry, minus 9.8. We don't have to multiply it by 1/2, so it's minus 9.8. I solve for that and I find out my time is equal to 1.37 seconds. So 1.37 seconds, I hit my apex. 1.44, I hit the wall. That means I have passed the apex. Yes, so I would write yes, I've hit the apex. I would hit the apex at 1.37, and we're past that time. Any problem that you get in this chapter is pretty much going to be a variation of that, and sometime you're going to find either how far the ball could go, or how high the ball could go, or how long it's in the air. So you're basically going to be looking for one of those 3 things. Our next problem is actually going to be way easier. In this one, we have basically like the one we did in class where the girl's pencil falling off the desk. In this case, we have 2 grenades. Grenade A and grenade B. They're thrown horizontally at different speeds off of a cliff. That cliff is 70 meters high. A has a speed of 2.5. and B has a speed of 3.4, both of those in meters per second. It's really nice. It tells us both of the grenades remain in the air for 3.77 seconds, which makes sense because all objects have the same acceleration due to gravity, and if we ignore air resistance, they're all going to fall at the same rate and hit the ground at the same time. So it makes sense if they're falling from the same place, they're going to hit the ground at the same time. What is the distance between A and B when they hit? So an object that's going faster is going to go farther. So B, and this is a funny looking line, is going to fall further. And A is going to fall here. So what is this guy? The way I would do that is I would just find out how far they each go. This one's going to be really simple because we know V is equal to D over T. And we can rearrange that and go velocity times time gives us our distance. They give me a time, and they give me two velocities. If I take 2.5 times 3.77, I find out that A goes 9.43 meters. And I find out that B, by taking 3.4 times 3.77, goes 12.82 meters. The difference between those being 3.4 meters. And that would be it. Sorry my marker writing was worse this time, I think. Some of my numbers look pretty bad, but hopefully you got the gist of what I was doing. Also, sorry my cat decided to knock over everything. See you guys on Thursday for lesson 2.